This is the PVA Position Velocity Acceleration Worksheet, Chapter 2.2. This worksheet, linear motion problems. So let's look at number 1. An object is traveling at 20 meters per second to the left. What is its speed and velocity? So 20 meters per second to the left. So we know that velocity has has direction. So left would be moving in the negative direction. Right would be moving in the positive direction. So 20 meters per second, the speed will remain 20 meters per second, but the velocity has a direction. So to the left is negative, so therefore negative 20 meters per second. Number 2, which has the greater speed and velocity? Object A with velocity negative 20 meters per second, or object B with a velocity of negative 10 meters per second. So if we compare these two, the one that has the greater velocity would be the value that is that is a greater value in terms of positive. So this negative 10 is closer to the positive value than negative 20. So this is a greater value than negative 20. So therefore, the greater velocity, or the velocity that is closer, that is greater in the positive direction, would be negative 10 meters per second. However, the greater speed would be the negative 20 meters per second. So remember, speed is the absolute value of velocity. So the absolute value of negative 20 is positive 20. The absolute value of negative 10 is positive 10. And 20 is greater than 10. So therefore, the greater speed is with object A. Number 3, a billiard ball is hit and travels in a straight line. If x centimeters is the distance of the ball from its initial position at t seconds, then x of t, this is the position function, 5t squared minus 4t. If the ball hits a cushion that is 12 centimeters from its initial position, so we're given a point that we can use later on, at what velocity does it hit the cushion? So we're trying to find the velocity at this moment in time. So we have our position function. Notice the relationship here, PVA, position, velocity, acceleration. Position is usually a lot of times the original function, and then if we find the derivative of position, we move on down to the velocity, and if we find the derivative of velocity, it'll take us to the second derivative, and the second derivative is acceleration. So we're trying to find the velocity at a moment in time, but first we need to find what the velocity function is. So we're given the position function. If we want to find the velocity function, we're going to find the derivative of position. So here we can simply apply power rule for this position function. So 5t squared, the power rule there would give us 10t. 4t would just give us 4. So here's our velocity function. Let's see, what else do we know? We know that the ball hits the cushion that is 12 centimeters from its initial position. So what we can do is we can set x of t equal to 5t squared minus 4t. If we want to find out at what moment in time the ball hits a cushion that is 12 centimeters away, we can set that equal to 5t squared minus 4t. So x of t is any position at a given time, and we want to figure out at what moment in time does the ball reach 12 centimeters. So what we can do is we can set 12 equal to 5t squared minus 4t. So we want to find out at what moment in time is the position going to be equal to 12. So the goal here is, if we can figure out the time at which this this event occurs, then we can use that to determine the velocity at that moment in time. Okay, so if we solve for t, we have to factor, bring everything over to one side. So I move the 12 over to the right side. 5t squared minus 4t minus 12 equals 0. If we factor, we get 5t plus 6 times t minus 2. If we solve for t, we get t equals negative 6/5, and t is equal to 2. In this case, we are only dealing with time that is greater than 0. So t seconds here. So we're going to ignore the negative 6/5. We're only going to use 2. So we know the velocity function going through power rule is 10t minus 4. So now we can plug 2 into the velocity function to find the velocity at that moment in time. 10 times 2 is 20. 20 minus 4 is 16. So 16 meters per second. Number 4, if a particle moves along a line according to the equation S of t, so S of t is another common notation for position function. In this case, this is x of t. Here we have S of t. Is t to the 5th minus 5t to the 4th for all real numbers t. So here we're dealing with t time values where we are also going to include negative values. Then how many times does a particle reverse direction? So particle is going to reverse direction when the velocity changes signs from either positive to negative or from negative to positive. So first off, candidates for when the particle reverses direction is when the particle is not moving or at rest. So when a particle is at rest, that is a potential point for a particle to potentially to reverse its direction. So first we need to figure out some candidates, right? When is the particle at rest? Well, particle is at rest when the velocity is 0. Okay, so we want to set velocity equal to 0, but before we can do that, we need to first find the velocity function. So we're given the position function here. We can go through power rule to get to the velocity function. So power rule, t to the 5th. Power rule, we get 5t to the 4th. And then 5t to the 4th, we can go through power rule there, bring down the 4. So 20t to the 3rd power. Okay, once we have our velocity function, we're going to set that equal to 0 because we want to find out the time at which the particle is at rest. So we set 5t to the 4th minus 20t cubed equal to 0. We can factor out 5t cubed. We're left with t minus 4. So we can set both factors equal to 0. 5t cubed equals 0. That means t equals 0. T minus 4 equals 0. We get t equals 4. So we put these two candidates, critical points, on the sign line, on the number line. And now we want to test the signs for velocity. When velocity is negative, that would indicate the interval at which the particle is moving to the left. If the velocity is positive, then that would indicate when the particle is moving to the right. So here we can test out a value. I'll test -1, for instance. If I plug -1 into the factored form, -1 would give me a negative here. -1 minus 4 is -5. So negative times negative is positive. So we know that in this interval, this particle is moving to the right because we get a positive velocity. Okay, here I can choose a test point. So I can choose 1. Okay, so here I chose -1. Here I'm going to choose 1, and here I'll choose 5. So if I plug 1 into the velocity function, because we want to find out the behavior of the velocity, whether it's moving to the right or to the left, into the factored form, so 5 times 1 cubed is 5. 1 minus 4 is negative, so positive times negative is negative. So we know that in this interval, the particle is moving to the left. Okay, here we can choose 5, a test point here. So 5 times 5 cubed will be a positive value. 5 minus 4 is positive, so positive times positive is positive. So we know that there's a change in sign at 0 and at 4 because the velocity changes from positive to negative and then from negative to positive. So not only is the particle at rest at time values 0 and 4, but because of the sign changes, these are also going to be times at which the particle reverses its direction. Okay. Okay, the position in meters of a particle moving on the x-axis is given by x of t, 2t cubed minus 2t plus 1. And here we're only looking at values for where time is greater than 0, so no negative values here. Find the acceleration when the velocity is 4 meters per second. Okay, so we're going to have to involve acceleration. So if we want to involve acceleration, we need to get to that equation first. So let's go ahead and set that up. So from position to acceleration, we need to go through derivative twice. From position to velocity, that's one derivative. That's the first derivative, and then we're going to go through the derivative process again to get from velocity to acceleration. So position, we can go through power rule. 2t cubed becomes 6t squared. 2t becomes 2. 1 is a constant. Derivative of 1 is going to be 0. Okay, so here's our velocity function. From our velocity function, let's go ahead and find the acceleration function. We know we're going to need it based off the question here. So 6t squared, power rule, derivative will give us 12t. 2 is a constant. Derivative constant is going to be 0. So we have our acceleration function. Find the acceleration when the velocity is 4 meters per second. So what we're going to do is we're going to find out the time, the moment in time when the velocity is 4 seconds. Once we find out the moment in time where velocity is 4 seconds, then we can use that time value to determine the acceleration at that moment in time. So what we're going to do is we're going to use our velocity function to find out the time at which the velocity is exactly 4 meters per second. So we're going to set the velocity function equal to 4, and we're going to solve for t. Okay, we want to find out the time value. So from here, we can add 2 to both sides, solve for t, divide both sides by 1. T is equal to plus or minus 1. However, based off of our problem, our condition, we know t is greater than 0, so we're not going to include t equals negative 1. Only t equals 1. So now we're going to use t equals 1 to find out the acceleration at that moment in time. We're going to plug 1 into the acceleration function. 12 times 1 is 12, so acceleration at that moment in time is 12 meters per second squared. This is the unit of measure for acceleration, meters per second squared, or units per time measurement squared. Okay, number 6, we have our position function given to us, t over t squared plus 5. Again, our condition here, time is greater than 0. At what instant of time will the particle start to reverse its direction of motion, and where is that instant? So we want to find out the moment in time when the particle reverses its direction. So just like number 4, we're going to determine when the velocity, when this particle is at rest by setting velocity equal to 0, and then from there we can determine through sign changes to see if there's any sign changes at that moment in time. So just because a particle is at rest does not guarantee that this particle will change direction. However, it is a starting point for us. If we can find out where the particle is at rest, where the velocity is 0, then that at least is a candidate for a potential place where the particle could reverse direction. So we want to set velocity equal to 0, but before we do that, we need to get to our velocity function. So we need to find the derivative of position function. So notice that this is in the form of numerator over denominator. So the most efficient way to get to our derivative, we're going to go through quotient rule. So quotient rule is f prime g minus f g prime all over g squared. So f prime is representative of the numerator, and g is the denominator. So f prime is a derivative of the numerator, that's 1, times the denominator, so t squared plus 5, minus the numerator, the original numerator, t, times the derivative of the denominator, so t squared plus 5 becomes 2t, and 5 goes to 0, all over denominator squared, so t squared plus 5 squared. Now if we clean this up, numerator we can distribute and combine like terms, so we get t squared plus 5 minus 2t squared. That leaves us with 5 minus t squared. Denominator is t squared plus 5 squared. When the velocity, we're looking for where velocity is 0. So velocity is 0, it's not going to make sense where denominator is equal to 0. When the denominator is 0, that would indicate where the velocity is undefined. So we're only concerned about where the numerator of the velocity is equal to 0. So if we set 5 minus t squared equal to 0, we get t is equal to plus or minus square root of 5. However, negative square root of 5 is outside of our domain. So we're only concerned about values to the right of 0, so it'll only be root 5. I put a 0 here to indicate this is a starting point for our particle, since this is kind of a boundary for our particle. So now root 5 is a potential point where the particle reverses direction, but to confirm that we need to test the velocity to the left and to the right of root 5. So we're going to choose a point. To the left of root 5 is 1. To the right of root 5, maybe we can choose 3. So if I plug 1 into the velocity function, numerator would give 5 minus 1 squared, which will be positive. Denominator is always going to be positive because it's squared. So positive over positive is positive. We know the velocity in this interval will be moving to the right because we have positive here. Here, if I choose 3 as a representative value in this interval, 5 minus 3 squared, so 5 minus 9, which is negative, over a positive. Negative over positive is negative. So the particle is moving to the right. It will stop at root 5. And then it'll continue, it'll change direction and move to the left. So there's a change in direction at t equals root 5. So we know that the instant in time, and then where is it at that instant, we would have to plug root 5 back into x of t. So we know that t is equal to root 5 is going to be the time, but then the location would have to be plug in by plugging root 5 into x of t. So if we do x of root 5, plugging root 5 into the position function, we get root 5 over root 5 squared plus 5. So that's root 5 over root 5 squared is 5. 5 plus 5 is 10. So root 5 over 10. So the position at this moment in time will be root 5 over 10.